Welcome, everyone. I'm Mario Sznaier from Northeastern University, and I'm going to talk briefly about the work we're doing on how to come up in real time with strategies for avoiding an active shooter, even if you don't know the environment, or the environment has drastically changed since last time you've seen it. And this is work we're doing with my coworker from Northeastern University, Milad, Siami, and our students. And I apologize, I have a really bad cold, so my voice could sound strange at some point. So the challenge that we're looking into here specifically is the limited situational awareness that decision makers may have when you're dealing with a threat that you may not have seen before, is intelligent, and you really don't have enough experience to decide what to do. And in particular, you may not have enough experience to project the consequences of a given course of action or strategy that you may come up with. And what we're trying to do to help here is to combine elements from machine learning and dynamical system theory and the psychology that Richard has talked about to come up with a decision support system that's supposed to learn models of crowds and threats. Those are models that are highly flexible, so you need to adapt them on the fly to the present situation on the ground, and then present a decision maker a slate of mitigation strategies and likely outcomes. We're not trying to take the decision maker out of the loop. We're just trying to make her job easier by saying, here we think the best strategies and what's likely to happen, and it's up to you to decide. But at least now there's more information. And obviously, in terms of relevance to the DHS enterprise, other than the main goal of SENTRY, you can use this exact same decision support to deal with natural disasters like the fast moving fires in LA, or you can use it even to do wargaming and discover vulnerabilities that you didn't know you had. So the top level, how this is going to work from a user standpoint, our input is going to be real-time multimodal sensor data. This is going to come from the video analytics from RA3, and this is going to come from the adaptive multi-sensor management from that David Castagnon mentioned. And then some sort of magic is going to appear, and the output will be a slate of suggested strategies and what are the likely outcomes. Of course, I mean, if you're an incident manager and I give you this, you shouldn't trust me. No one should trust something that says magic unless you are allowed to look inside a box and you have certificates that what's inside a box, it's something reasonable and that makes sense rather than maybe some poorly designed heuristics. So when you actually open the box, here's what we're doing. We're working under the assumption that we have a guiding agent paradigm. That means there's a person in or set of persons in the crowd that actually can guide it. Could be, say, a teacher in a room. If you're in a stadium, could be ushers that guide the people, but someone is receiving information in real time and acting on that information. We're develop adaptive models of crowds, threats, and the guiding particles. So those are equivalent to the models that Richard just talked about, except that we don't use agent-based models. We are trying to come up with probabilistic mathematical descriptions. And once we have those math descriptions, we're going to use them to come up with what we think are safe guiding strategies that we're learning based on the situation on the ground. But the last step, as always, it's a sanity check that actually tells you what's the safety margin if you were to pursue that strategy. And as I said, at the end, we're going to give you a slate of suggested strategies. For instance, think about as a set of waypoints for the guiding particle to go, and a likely outcome saying, if you follow this with certain probability, you're safe, or maybe there's a certain probability of casualties. So what I'm going to do is I'm going to touch very briefly upon some of the points in here, or some of the elements that go inside this box. So Oh, sorry. In terms of the model, our math model, again, this is equivalent of the agent-based model that Richard was talking about. It's what we call a predator swarm guide model. This has been inspired by the type of behavior that's being observed in nature when you have a swarm of particles that's been attacked by a predator. So in here, we're modeling the crowd as a set of particles, and that's guided by the first equation here. And here, what this model is the fact that people in the crowd are attracted to each other or repelled. They are attracted or repelled by the actions of the guiding particle, depending on the level of thrust, and certainly repelled by the predator. The second equation here actually models what we think the guiding particle will do. On one hand, the guiding particle is trying to get away from the predator. On the other hand, it's trying to get to safety. And the parameter lambda here models or balances the attraction to safety versus repulsion from the predator. And the last one, it's a predator that's just going for the throat, trying to go and get in the middle of the crowd and kill people. What makes this model interesting is that since it has lots of adjustable parameters, it encapsulates a very rich set of behaviors that we believe cover most of the behavior of real people in active shooting scenario. And the other thing that's interesting here is that what we observe is that the predictions of the model are very highly dependent on the values of the parameters. And this is something also that Richard observed in his agent-based model. So the reason this is useful is that it opens a possibility that maybe you can change the values of those parameters by doing pre-event training. So for instance, train people to either disperse or cluster, or train people to follow closely or loosely the instructions of the guiding particle, and so on and so forth. Now, to show you that this actually makes sense, here's a simulation of a shooter going into the crowd. And by no means, this is an optimal strategy. As a matter of fact, this is probably the worst one, because what you see here is that the guiding particle just makes a mad dash for the output or the exit, doesn't care at all what happens to the crowd. And as you can see, a lot of the crowd actually gets killed. And this is illustrated on the graph on the left, where on the horizontal axis, what you see is the strength of attraction of the guiding particle to the exit. In other words, on the right-hand side, when lambda is maximum, it means that the person makes mad dash for the exit without taking into account what happens to everyone else. And as you can see in the middle, there's a sweet spot where you have to go towards the exit, but avoid the predator. So this is the type of things we hope to get out of our model that will give guidance on how to minimize the number of casualties. Okay. Now, one of the things that I mentioned in the past slide is the fact that the strategy for the predator was for the guiding particle was not optimal. So one of the things we've been looking into is how do we get an optimal guiding trajectory for the particle that avoids a unsafe set. So in here, just for this slide, I'm going to assume that the unsafe set is static. So in other words, if you get inside the red circles you see in my slide, you're dead. And what we're trying to do is we're trying to give a trajectory for the guiding particle that gets to the goal, which is the lower left side of the plot, without getting into the danger zone. Okay. From a mathematical standpoint, what we do is we take the model that we had before that has lots of adjustable parameters, and we don't know the values of the parameters ahead of time. I mean, we may have some idea of the cohesivity of the crowd or how much they trust the guiding particle, but we actually have to infer the values of those parameters from the data that we're seeing. So we'll observe the crowd for a little bit and use that information to come up with strategies that are guaranteed to work for all possible values of those parameters. Now, This is unrealistic in the sense that, of course, the shooter is not going to stand there and wait for people. So what you need to do is you need to deal with the case where you have a moving active shooter. So what we did is we took our framework and we generalized it to the case where now the active shooter moves. So you can think of the red circles that you've seen in the past slide and now move them in an adversarial way. And we managed to actually extend the framework to avoid being killed. So what you're seeing in the graphics is blue is a guiding particle, red it's the shooter, and if you get inside a small red disk, you're dead. And you can see here, the guiding particle barely escapes the shooter. I mean, the head of the blue trajectory is always outside the small red disk. Okay, so this is sort of a very cartoonish illustration of what you'll get. You'll either get a certified trajectory saying for all possible pursuer moves, you'll be safe, or it proves that unfortunately there are no safe strategies, so you may have to switch to maybe shelter in place or be willing to accept casualties. Okay, we're very happy with these results, but the caveat in here is that we assume that we had perfect knowledge of the environment. Okay, now what happens if you have more complex environments or you don't know what the environment looks like ahead of time? Then computational complexity explodes. So what we're looking at, it's an alternative based on very recent developments in machine learning. If you know what generative AI means being able to generate elements from a given set. And the set that we're interested in generating here is a set of safe trajectories from where you are to the safe region. So offline, we learn a set of possible trajectories for different configurations of the space and for different locations of the potential threat. And online, we actually sample from those trajectories condition on the location of the threat. So here's an example of what happens. Gray squares here are obstacles that were known ahead of time. Red circles were obstacles that were not known ahead of time and need to be avoided. And in the far left pane, what you see is the trajectory is being planned from the top, which is present location, to the bottom. Okay, and as you can see, the trajectory already avoids some of the unknown obstacles. Then in the second pane, what you see is a red disk. It's a shooter. However, the particle doesn't know that the shooter is there. You don't know that the shooter is there until you enter the orange disk. That's the sort of your field of view. And in the third, fourth, and fifth planes, you can see that in real time, we adjust the trajectory so you actually end up avoiding the shooter and getting to safety. So compared to what I showed you before, in here, we have two different approaches. One that gives you hard certificates, but requires known scenarios. The second one, based on new AI methods, it's probabilistic. So it doesn't give you a hard certificate, but gives you a probability of success. And it's a lot more flexible because it's actually being able to incorporate obstacles and in real time. Okay. So, and I don't really have time to cover this, but this is a certification part where we look at the probability distribution function of the crowd as time goes by, and we measure how close the crowd will get to the unsafe set as a function of time. And it's for you to decide if that safety margin is enough. Okay. What are we doing next? We want to expand our PSG model to consider emotions, and that's where we're working with Richard. And we also like to have a more intelligent attacker that can exploit vulnerabilities. Okay. And one thing that's key to this is the ability to learn in real time the emotional state of individuals. So I want to say many thanks to the audience. This has been the work of lots of students. Obviously, many thanks for DHS for posing the problem and funding this. And special thanks for all the SENTRY support staff that works very, very hard to make all of this possible. So that's it. Happy to answer any questions.
So Mario, one quick question. What was most surprising about the results that you have?
How the variability of the results based on the parameters of the model, that just changing a little bit the parameters of the model, you can go from 90% casualties to almost non-zero casualties. So this is also, I think, that something that Richard noticed is the trust that people have in the guiding particle or on each other, whether or not they know each other and they follow each other, or it's everyone for herself, has a huge impact on survivability.
So in looking at Richard John's agent-based results, which are real humans, acting to a given scenario, how does that dovetail with what you're finding?
I mean, I think we're seeing the same thing. And for us, I mean, we came up with this PhD model not entirely out of the blue, but this is known in biology. I mean, we had no reason to believe that humans will follow the same one. And we're very happy to see that Richard's results actually support this. So our next step is to actually see how we can use Richard's results to learn the parameters of the model by looking at the crowd.
Mm-hmm. Thank you.
Thank you.